Okay, our last option of the day, or last option of this lesson on optimization. We're going to try a problem that should be familiar from last year. Nope. Nope. I used to. Like, I would say when I first started teaching for about the first 13 years, I thought people remembered stuff from previous years. And now I realize that that's fiction.
Because your memory decays. Like, that's the only thing I remember. We're doing a memory decays.
Okay, do you have this problem in your notes regarding the dimensions that give the largest area? Okay. So as soon as everybody's quiet, we'll give it a start. Thought you were on a cruise. Just Ava? Yeah. Okay, so we're going to take a parabola shaped like y equals 12 minus 3x squared, and we're going to put a rectangle on the inside. We want to know the dimensions of the rectangle that give the maximum area. So what does that 12 minus 3x squared look like? Very good. Yep. Now, if you wanted to, you could identify that this distance is 2, that's negative 2. Up here is 12. You don't have to do that. But we are going to take a rectangle and place it right on the inside. And I'm going to show you that it passes through a coordinate on the parabola called xy. So you've now seen a number of these types of problems. Maybe not this exact one, but it's time for you to start kind of guiding me as opposed to me guiding you. What formula should I write down? Okay, good. So you're saying area is equal to, we'll say, the length of the base times the height, or length times width. Either way you want to write it is fine. L is exactly right. Base times height. So I got two different variables there. What's the length of the base? Definitely less than 4, right? Close. What? 2x. Why? You got x this way and you got x that way. So the base has a length of 2x. See? I was wrong. Sometimes we do remember things from previous years. So saith Timothy. What is the height? So this is the x coordinate. So if you know you got xy, so you went x units that way, and then this would be negative x over there. So the distance between negative x and positive x is 2x's. Does that help a little bit? Okay, what's the height? Y. Great. So that does not help us at all because, as you can see, that is a different variable. I need an x over there, folks. Yeah, y is 12 minus 3x squared. Now, if you would like to go ahead and use the product rule here to find the derivative, you could, or you could just multiply and get area is equal to 24x minus 6x cubed. So area prime, or the derivative, is what? Good. What shape does that make? It's parabola. Upside down. But if you look at the original function, what does that make? Yeah, makes it cubic like this, right? So how many spots does that have a derivative equal to 0? Twice. So you're looking for the first one or the second one? Why the second one? Because we're trying to maximize. Very good. So I'm going to solve this. 0 equals 24 minus 18x squared. or 18x squared is equal to 24. So let's come up with a decimal. X squared is 4 over 3. So if I take the square root of 4 divided by 3, and I get 1.15. Yeah. Does that answer our question? The question is the length of the base and then the height. If x is 1.15, what's the length of the base? Twice that, so 2.3 by, and then we're going to plug it in, right? 12 minus 3 times, do I plug in 1.15 in for x or 2.3 in for x? 1.15, it says that's what x is, so 1.15, and I square that, and I get 8.03.
How do you get y?
It says y is equal to 12 minus 3x squared.
Oh.
Sir?
How did you get 1.15? Or, I know I do 1.15, but how did you get 2.3?
So the base is twice the x value. So I doubled 1.15 to get 2.3.
Okay, then you do the. Okay, then 8.3.
Yep. You got it. Wall shame for Kaylee?
Yep.
We didn't see you do the chicken dance. Okay, all right. We'll let her off. All right, so there's an example for you. I'd like you to move to problem number 6. Find the equation for a line tangent to this curve that has the largest slope. What I would like you to do is I would like you to just see if you could just draw the picture and try to make any sense of this problem before we start it. Draw the pictures, try to make any sense of this problem before we start it. Go. Five, four, three, two, one, and we stop. Hopefully you drew this picture. You see that it's negative. And then it says where it has the line tangent has the largest slope. So can you visualize here where the largest slope is?
Yeah.
Right there? Yeah. That's where the largest slope is, right? See if you can talk to your peer. I know you don't remember things from last year, but hopefully you can remember something from the last unit. What special spot do we call that on the graph? Talk. Go. Kendall, what is it? It's the inflection point. How do we find the point of inflection? The second derivative, right? So I'm going to find the first derivative. What is the first derivative?
2 minus 6x minus 12x minus 9x.
So I have a first derivative. What does a first derivative tell us?
Point of max.
Okay, it can tell us maximum and minimum, can tell us increasing and decreasing. But what we first learned is that doesn't the first derivative just tell us about slope?
Where did the 18
Oh, sorry. Thank you. All right.
Three.
Oh. All right. So now let's find the second derivative. What's the second derivative? Okay, and we know that this tells us concavity and inflection. Oh, thank you.
Wait, I have a question.
Yeah.
What was the answer to the question you were asking us about what is the first derivative tell us?
Yeah, so the first derivative tells us about maximums and minimums, tells us about increasing and decreasing. But first and foremost, the first derivative tells us about slope. Now, you did tell me that this tells us about inflection, which is good. So I can determine inflection. Notice that that graph has the shape of a line. And the line, does it go up or does it go down? It goes down, looks something like that, right? And so what is this spot where it crosses the x-axis? It's -2. So if you were to solve this equation equal to 0, you would get -2. So that's helpful for us. But we need an equation for a line. What two things do we need for an equation for a line? Slope and a point. Okay. So the slope and the point, I have a -2 value for x. How do I come up with the y value? Where? Into the original function right here. That's what I'm going to plug it in. 2 times -2 is -4. -2 squared is 4 times 6 is 24. And then -2 cubed is -8, so it'll be 8 plus 8. Be -20. I need slope. What do I use up here to produce slope? That first derivative right here. So I have -2. That will be 2 plus 24. And then it will be a -12. Which will be 14.
But you plug in -2 here, right?
Yep. So I now have enough information here to write my equation. Y, what? Plus 20 is equal to? Good. Or y plus 20 is equal to 14x plus 28. Or y equals 14x plus 8. And when we look at the problem from the beginning, we could see that it should have positive slope, we would say. 14 seems like a reasonably high number, so I'm guessing that's it. Any question? Going once, twice, 3 times. Okay, we're going to skip problem 7. We move to our very final problem. Is that it? Then we move to problem number 5.
Brittany told me you kept saying your mom. And she wasn't saying your mom.
Okay. A rectangle is inscribed in a semicircle of radius 16 inches. What dimensions of the rectangle? What dimension should the rectangle be in order to maximize the area? See if you can start setting any of it up. Any of it up.
What's going on today?
What?
Dimensions should the rectangle.
Oh.
What should the dimensions of the rectangle? It was good.
It was fine the way it was. Oh, just reading too quick. All right, all right.
This was for you in the bathroom.
Huh? No.
Oh no.
Did you at least draw that?
Got 8 to
I didn't draw them.
Okay.
Why do you have 16s everywhere? Oh.
So a radius of 16 means that from the center of the circle to the outside is a measure of 16.
Oh.
Okay?
Oh.
If it said diameter, then you would put 8 and 8. But this is a radius of 16. Okay? What'd you write down for your formula?
I didn't write it down.
Area is equal to base times height. Same as the problem we saw before, right? What is the base? No. 2x. What's the height? Okay. Very good. Great. So we'll use J as a really good idea, and instead of putting Y, we'll just plug in something else, right? So what is that?
Whatever the radius is. What if we find the area of the semicircle?
There's no function here, is there?
No.
Hey.
At least they tell us it's a semicircle, right? Who knows the equation for a circle? Don't say pi r squared. That's the formula for area of a circle. It's not what we're talking about. Don't say 2 pi r. That is the circumference. What is the Cartesian xy equation for a semicircle? Luke. Very good. Luke has it. X squared plus y squared is equal to r squared. Talked about it last year about 28 times. And that is an equation for a circle. If you remember the circle of life, the unit circle. Okay. Now, in this situation, you know what r is. What is r? So therefore, you have x squared plus y squared is equal to 256. Because 16 squared is 256. Tell me now, as you look at this problem, what is it that we can do to solve for y?
Solve for either x or y.
Good. So I have y squared is equal to 256 minus x squared. And then what do we do to both sides? So we get the area is equal to 2x times the square root of 256 minus x squared. So the common mistake that we tend to do is we just take the square root of each. Just think about this. If you had the square root of 25 minus 16. So what is 25 minus 16? And what's the square root of 9? 3. But let's propose our new method of mathematics. Let's take the square root of 25 is 5, and the square root of 16 is 4. You get 1. See how that does not work out? Very illegal to take a root and distribute it over subtraction in that way. Can't do that. Okay. All right. So what do we do with that? Do you know what that shape looks like?
No.
I don't really know either.
Well, can't you just do the product?
You could do the product rule to find the derivative. So let's do that.
Oh.
A prime is equal to, what is the derivative of 2x? Dos, which is Spanish for 2. Plus 2x times what? I got to do the chain rule. What goes on the outside? U to the 1/2. What goes on the inside? Okay. What is the derivative of u to the 1/2? And the derivative of 256 minus x squared? Negative 2x. When we multiply those, notice what's going to happen to the 2's. They will cancel. What I get a positive or a negative? What's going to be in the top? A negative x, and in the bottom, I have the root of 256 minus x squared. That's a little bit ugly, but we are going to solve it equal to 0. Notice on the top, I'm going to write 0 is equal to, I'll write 2 roots of 256 minus x squared over 1 minus what goes in the next numerator? 2x squared. And what's in the denominator? Okay, so notice that I tried to set this up for you in the previous test where we're dealing with these type of derivatives to solve these type of problems. So as we look at solving that, we want to create common denominators. So I'm going to multiply the top and bottom by root of 256 minus x squared, root of 256 minus x squared. And so what are you going to get in the top? And what is 2 times 256? 512 minus what? 2x squared minus 2x squared. Okay, let's look at what's really, really interesting about this problem, okay? Where's the denominator equal to 0? For what values? 16. Would you guys agree that it's at both positive and negative 16? Now look at what happens with the problem at those values, okay? What do you notice about the slope at negative 16?
Hold up. How do I know 16?
It's 256 minus x squared. So what number do you square to get 256?
Everyone knows it up top.
It's just because we've used it 4 times. So, okay. So I get it. All right. Better? Okay. So notice how it chooses 16 and negative 16, namely because you get vertical tangent lines on the ends there. So the slope is undefined. Okay, so it picks those points out. Also notice that if you did go all the way out to positive 16 and negative 16, there would be no area, would there? Okay, so it's interesting how it sees that. The other piece that it sees is where the top is equal to 0. So I don't really need to focus on the bottom. We've already done that work, but let's just focus on the top. And we get the 0 is equal to 512 minus 4x squared. How are we going to solve that? Good. So 4x squared is equal to 512. X squared is equal to 128. And we take the square root. And I get, what, 8 roots of 2? Let's take the square root of 128 just to verify. I have the square root of 128, and I get 11.314. The denominator, we talked about that's where the derivative is undefined, and so that is where I have vertical tangents on the end. That will produce a 0 area. So I have x is 11.314. Does that answer the question?
No.
The question is, what should it be in order to maximize the area? What should the dimensions be? So if x is 11.314, what's the length of the entire base? How would I determine that? Double it, and we get 22.628 by, and then how would I come up with the height? Yeah, we had this great equation of y is equal to the square root of 256 minus x squared. That will tell us the y value. And as I take out my calculator, I'll try that. Yeah. Which part? So earlier we solved for y and we got the square root of 256 minus x squared. So I turn it on, I square root, and I have 256 minus 11.314 squared. And look at the interesting result.
Oh my gosh. That was insane.
Yeah, and it just so happens that in order to maximize the area, you need to have a perfect square here that's 11.31, and a perfect square here that's 11.31, that is in fact what will maximize it, which is kind of interesting. The other interesting thing that I would like to show you is the original function. I just want to type that in so you can get an appreciation for it. I think you guys will like this a lot. If I take 2x square root of 256 minus x squared, and I'm going to change my window because I need that. I know I need to go out to 16. Look at my graph here. Don't see too much right now, do you? Okay. I'll change my window to make my y values a little bit different. We'll go negative 200 to positive 200. See if we can see it then. And we'll go 100 for my, let's see if we see it now. See a little bit of it now? Let's make one more adjustment here to the window. Instead of going to negative 200 and positive 200, let's go to negative 600 to positive 600. And you tell me what that graph looks like. Half of an infinity symbol. We could even complete the other half.
Oh my.
Yeah. It's actually an example of an infinity graph. Yeah. It's kind of cool. Really pretty. All right. Take out your homework. Let's talk about what you can do, what you can't.
I can't do it, man. That's what I can do for you. The article that I'm using, the title is Tits Up. I'm not even sorry. And I did this for movies for everyone. I think it was like, stop saying movies. Stop it. You know, I'm good. Personally, it's not for me. Why didn't you just say 1 to 8? Because 6 is oh.
Okay, just to give you guys an idea, so some of you might connect a little bit more with this than others, that's fine. Without a doubt, you have to do problems 1 through 5, 7, and 8. If you note, problem 1 and 2 were basically identical to what we did in the notes. Problem 5 is basically identical to what we did in the notes. I think we did, 3, 4, and 8 together in class. So we're not actually asking all that much, more or less, for you to kind of follow and appreciate it. If you are looking for a challenge, problem 6 is a nice problem. This problem is usually required in previous years. It is a problem that I've always put on tests in previous years. I forgot to put it with the notes, so we didn't cover it. But that's a good challenge problem. 9 through 11 are just flat out beautiful. I mean, they are awesome. Number 9 is a classic gutter problem. What shape should we make a gutter in order to maximize the volume from a finite specs for a piece of tin, which is great. And there's the closet or the hallway problem where you're bringing a pole down a hallway. What's the longest length of a pole you can bring given the constraints of the hallway? Good types of problems. The one that I don't have in here, and we're not going to have time to do as a class just because we've kind of lost a day in our third quarter, or our second quarter is a very, very short quarter. But usually I do take the class just one day through the artery problem. I mentioned you guys before, but the idea was, suppose that an artery is blocked and you have to do a what? A bypass. The question was, at what angle should we place the bypass? What theta should we place the bypass in order to minimize the viscosity of the blood flow? And so that's something that I usually, if we have time, I take the calc class through. We don't quite have time for that, but I'll post a link to the video in case you're curious and want to see it. So, everybody good? All right. It's your time. which isn't a lot. But thank you for your